Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and help us out on Patreon if you can. We also have gifts available in the Academy store. There are links in the description. In one of our lessons, we suggested that the United Launch Alliance should ask Elon for 3 Raptor engines to replace the 2 Blue Origin BE-4 engines that continue to be delayed. Some of you objected to my suggestion that SpaceX should help ULA.
Blasphemer!
Well, if that annoyed you, today's lesson will make you apoplectic. But first, let's review how we got here. In 1969, a task force had been appointed by President Richard Nixon to determine America's future in space. The Apollo program had been a great success. At that time, America had the most powerful rocket on Earth and the only spaceship capable of leaving Earth orbit, with a lunar lander that gave Americans access to the moon. The task force came back with the following recommendations. America needed a personnel shuttle, a space station, continued manned moon landings and a base, leading up to a mission to Mars. President Nixon did not like this recommendation. NASA's budget had been cut from $5.9 billion, which was 4.4% of the federal budget, to $4.25 billion, or 2.3% of the federal budget. From that list, President Nixon picked just one project, the Space Shuttle. Early plans for the shuttle had been mainly as a personnel carrier, like the NASA HL-20 discussed in this lesson. But by 1972, Nixon had cut NASA's budget even more, down to just $3.4 billion, which was 1.6% of the federal budget. This put everything in jeopardy. The original shuttle design was for a fully reusable 2-stage vehicle that would have pilots in both stages. The first stage would reach hypersonic velocities and release the second stage at an altitude of 15,240 meters. The first stage would then go back to land horizontally, while the second stage continued to orbit. But the budget cuts doomed this plan, and instead of a fully reusable system, we ended up with this. This is the Space Transportation System, or shuttle as we all know it. 2 solid rocket boosters that would return by parachute into the ocean and be refurbished. A large propellant tank holding oxygen and hydrogen that would be thrown away. And a large space plane that would have to carry both payload and personnel. The propellant in the large tank would be pumped through the shuttle to be burned in the powerful and efficient RS-25 rocket engines. The first space flight for the shuttle was on 12 April 1981, and the last was on 8 July 2011. 6 shuttles were built. Enterprise, which was a prototype for glide tests only. Then Atlantis, Challenger, Columbia, Discovery, and Endeavour. Columbia was the first to fly, and Atlantis was the last. This was America's only way to get people to space for 30 years. And it had turned out to be quite expensive. In fact, the cost of a space shuttle launch ended up being about $450 million per mission. Of these 5 ships that flew to space, 2 failed with complete loss of life. Challenger exploded on launch, and Columbia burned up on re-entry. After the last shuttle flight, America had no way to get humans to space, depending on the Russians while we got our act together. The solution was supposed to be the Space Launch System, created by an act of Congress to return America to supremacy in space. The SLS, as it usually is called, was supposed to be a fast way to get Americans back into orbit and to the moon, using much of the existing shuttle hardware. 4 of the RS-25 engines would be placed on the bottom of the central tank, similar to the Soviet Energia design. The solid rocket boosters would be improved, and another segment added, going from 4 segments on the shuttle to 5 on the SLS. They also scrapped the parachutes, as it wasn't really saving money to recycle the boosters. And they improved the polybutadiene acrylonitrile propellant. The massive hydrogen and oxygen propellant tank used on the shuttle, called the external tank, had been 47 meters tall and 8.4 meters in diameter. In the nose was the liquid oxygen tank, 15 meters tall, with anti-vortex baffles. This was connected by an intertank to the liquid hydrogen tank, 29 meters tall. These were made of advanced aluminum alloy and got lighter over the years. Because of the density difference between liquid hydrogen and liquid oxygen, the volume of the oxygen tank, 831 cubic meters, is a little more than half that of the hydrogen tank at 1,607 cubic meters. But because oxygen is much denser, it had a lot more mass. The stoichiometric oxidizer to fuel mass ratio would be 8. But like most rocket engines, the RS-25 runs fuel-rich at about 6. The shuttle had 3 RS-25 engines. These have a maximum thrust at sea level of 1.86 meganewtons, or 190 tons as Elon prefers. That would give all 3 engines a total thrust of about 570 tons. This was not enough to get the ship safely off the ground without the solid rocket boosters. These each added 16 meganewtons, or about 164 tons of thrust each. The Space Launch System used much of this hardware with modifications. The central core tank on the SLS is much bigger, at 65 meters tall. They are able to make it taller by adding extra barrels down here. A barrel is one of these sections, and then making a larger oxygen tank up here. Despite its impressive size, it only has a dry mass of 85,275 kilograms. The volume of the oxygen tank is about 742 cubic meters. The liquid oxygen mass is given by NASA as 847,364 kilograms. This gives our expected density of 1,142 kilograms per cubic meter, which corresponds with a temperature of 90 Kelvin, or minus 183 Celsius. SpaceX likes to cool theirs down a little further, ending up with a density of about 1,250 kilograms per cubic meter, I'm told. The hydrogen tank has a volume of about 2,030 cubic meters, and a mass of 144,130 kilograms, giving us the expected 71 kilograms per cubic meter for the density of liquid hydrogen at the colder 70 Kelvin, or minus 203 Celsius, at which it must be stored. With 4 RS-25 engines, the SLS core stage will have a maximum thrust of 7,440 kilonewtons. Let's pause for a second. The mass of the core stage itself is a total of 1,064,727 kilograms. If we multiply that by the force of gravity on Earth, 9.807 meters per second squared, we get a total weight of 10,441,778 newtons. With this weight, and a total thrust of 7,440,000 newtons, the core stage, like the shuttle and external tank, cannot launch on its own. This brings us back to the solid rocket boosters, or SRBs. For the shuttles, these were 45 meters tall and 3.7 meters in diameter. These were assembled in sections, as you see here. 4 sections for the shuttle SRBs, which have been extended to 5 sections for the SLS. The SLS SRBs will have a dry mass of 84,000 kilograms and a propellant mass of 709,000 kilograms. This gives a total mass of 793,000 kilograms. The shuttle SRBs produce 16,000 kilonewtons per booster. The SLS SRBs have been ramped up to 20,000 kilonewtons each. The 2 SRBs alone will produce 40 meganewtons of thrust. The solid rocket boosters are how the Space Shuttle and now the SLS will get off the ground. The SLS will have a third stage. There are several versions planned. The largest is called the Exploration Upper Stage. This is planned eventually to use 4 RL-10C expander cycle hydrogen-fueled engines. These are right now the most efficient rocket engines on Earth, with 462 seconds of specific impulse in vacuum. The exploration stage will be up to 18 meters long with a diameter of 8.4 meters. It will have 129,000 kilograms of hydrogen and oxygen propellant. This would be a very capable superlift rocket. But before we get to this, we have to start smaller. Let's look at what is planned for the first few flights of the SLS. The first 3 missions are designated Artemis 1 through 3. These will use an interim cryogenic stage. An interim cryogenic stage is much smaller than an exploration stage and uses only one RL-10B engine. With a length of 13.7 meters and a diameter of 5 meters, it has a dry mass of 3,765 kilograms. Add in the interstage, and it's closer to 5,000 kilograms. The propellant mass is 26,853 kilograms. The burnout mass is given as 4,354 kilograms. This is more than the dry mass. It is always the case that you don't get to burn every bit of your propellant mass. There will be gas you can't pump, liquid sticking to pipes, and for solid rockets, slag that sticks to the walls. Here we see an exploded view of this with an Orion spacecraft. Here you can see the boosters, the core stage, the first stage adapter, the interim cryogenic propulsion stage, another stage adapter, and a spacecraft adapter. Then the panels covering the service module for the Orion, the service module itself, which will have the solar panels, the crew module, and the launch abort system. If everything works as planned, this will launch humans to the moon. But everything has not gone as planned. Instead of being cheaper than the shuttle, this has cost about $30 billion so far. It was supposed to fly in 2016, but is still on the ground. If you build a complicated machine and wait years to launch it, things break down or need to be upgraded. The latest delay was to upgrade the main engine controller, or MEC. This is a computer that controls the rocket engine, and each engine has one of these. NASA is talking about this thing flying multiple missions into the middle of this century. I'm not so sure. The first SLS has been assembled for the Artemis 1 mission, which was planned for the end of 2021, but again has been delayed. Artemis 1 will launch an uncrewed Orion around the moon and return it to Earth. If all goes well, Artemis 2 will launch with a human crew to orbit the moon and return. Think about that. Even though the RS-25 engines and solid rocket boosters are proven technology, there have been a lot of upgrades and modifications, and software revisions. And who built most of the SLS? That's right, Boeing, the company that completely failed with the Starliner spacecraft due to faulty software and leaking valves, will be trusted to make a rocket so dependable that it can carry humans on its second flight. I know that people like to think of Elon as a risk-taking cowboy, but no human being will launch on a Starship until the Starship has flown at least dozens of times. I love space, and I would love to travel in space. I wouldn't mind having my ashes scattered in space, but not on my first mission, when Boeing blows up my Orion capsule with a faulty valve. The true cowboys are whoever thinks this is a good idea. But what could we do with this massive rocket system so that it wouldn't all be a waste of taxpayer dollars? Let's see. The core stage has a total mass, with its engines, of a little less than 1,065 tons. Do you know what is being built to lift 1,320 tons off the ground? This guy. Let's take a look at this. The latest numbers I can find show the Super Heavy booster now holding up to 3,600 tons of propellant. Let's plan on only 3,400 tons of that, as we have been using. And it says a dry mass between 160 and 200 tons. We will go with 180 tons as we have been. The total mass should be 3,580 tons for the booster. The Starship has a dry mass of 120 tons, plus 1,200 tons of propellant, plus 100 tons of payload, bringing the second stage Starship mass to 1,420 tons, and the entire Starship system mass to 5 million tons. The SLS core stage is only 1,065 tons. That leaves room for a 355-ton third stage. The booster has 29 Raptor engines right now, but is planned to go up to 32. Each producing a maximum of at least 2,200 kilonewtons of thrust. That's 224 tons of force in Elon speak. Maybe more if recent statements hold up. With 32 engines at full power, we would have 70,400,000 newtons of force. Our ship has a mass of 5 million kilograms, therefore a weight of 49,035,000 newtons, giving us a thrust-to-weight ratio of 1.44. Very respectable. The Super Heavy lifts off the ground with the SLS core stage and third stage on top. This thing will be rapidly burning fuel. The sea-level Raptors have a specific impulse of 330 seconds. We use our formula for turning specific impulse into exhaust velocity and get a value of 3,236 meters per second. Now if we rearrange our force equals mass propellant flow times exhaust velocity formula, we can calculate the mass propellant flow. 70,400,000 newtons of force divided by 3,236 meters per second equals 21,753 kilograms per second. As the mass drops, the thrust-to-weight ratio would improve as we climb. If we stayed at this power setting, we could burn for 156 seconds. At the end of our burn, we would have lost 3,400,000 kilograms of mass, giving us a final mass at main engine cutoff, or MECO, of 1,600,000 kilograms. If we don't throttle down the engines, we would reach a force of 4.5 Gs at MECO. I don't know the stress limits of SLS core stage, and we might have to throttle back to reduce the risk of damage to the ship. If we did, we would spend a little more time in gravity drag and have to burn longer, reducing our efficiency a little. Our initial mass was 5,000 tons, or 5 million kilograms. Our final mass is 1,600 tons. Our exhaust velocity is 3,236 meters per second. Using our formula for delta V, we get a value of 3.69 kilometers per second. Remember, we are shooting for 9.4 kilometers per second to get to a stable low Earth orbit with a final orbital velocity of about 7.8 kilometers per second. We still need a little more than 5.71 kilometers per second. The empty booster falls away, bringing our mass down to 1,420 tons. This is our new initial mass for the second stage. The Space Launch System core stage fires. This core stage, burning hydrogen, has a much higher specific impulse than the methane-fueled Super Heavy booster. With a specific impulse of 452 seconds, we get an exhaust velocity of 4,433 meters per second. The total propellant mass of the core stage is 979,452 kilograms, or a little more than 979 tons. Let's say we can burn 975 tons of that. That will leave us with a final mass of 445 tons. This produces a delta V of 5.14 kilometers per second. We needed to produce about another 5.71 kilometers per second of delta V, and we came up only 569 meters per second short. The second stage separates and falls away, carrying away 90 tons of core stage and residual propellant. That leaves us with 355 tons. This is the third stage, and it is using the more efficient RL-10C expander cycle hydrogen engines, with a specific impulse of 462 seconds. That gives us an exhaust velocity of 4,531 meters per second, and since delta V equals the exhaust velocity times the natural log of the initial mass over the final mass, we can solve for final mass. Delta V over exhaust velocity equals the natural log of initial mass over final mass. E to the power of delta V over exhaust velocity equals the initial mass over the final mass. The final mass times E to the power of delta V over exhaust velocity equals the initial mass, and the final mass equals the initial mass divided by E to the power of delta V over the exhaust velocity. E is a constant with a value of about 2.718. This gives us a final mass of a little more than 313 tons. What could we do with 313 tons in low Earth orbit? Going from low Earth orbit to low lunar orbit with capture burn is about 4,100 meters per second. We could fly this with RL-10s and reach lunar orbit with almost 127 tons. It takes about 2,000 meters per second of delta V to safely land on the moon. Using RL-10s again, our same equations tell us that we could land on the moon with almost 81.5 tons of mass. That's one flight, not needing any tanker flights, and if we have some RL-10s mounted high on the ship, no giant elevator to get you to the surface. Something to think about. Thanks for listening, have a great holiday, and stay safe. At Astra Pro Terra.